Hi. This presentation aims to integrate a number of different themes that I've been working on, specifically how to increase collaboration within an open source electronic healthcare platform. In this case, that's OpenMRS, Open Medical Records System. And specifically, the presentation will propose how increasing modularity can be a critical element in being able to build a platform where it's easy to collaborate. And so we'll talk about horizontal and vertical modularity and this impact that it can have on the governance and collaboration of an organization. And today, there's three main components to the presentation. The first part is on perspectives on OpenMRS, and we'll look at the ongoing conversations about what people want in the future of OpenMRS, some of the wish list items, and apply an overarching narrative of how fragmentation has played into this. In part two, in principles of modularity, we'll highlight the role that modularity has in the physical world and the organization of companies, and why modularity makes sense in an open source or just in any electronic healthcare record. Part two will end looking at specific examples of horizontal and vertical modularity and a quick mock-up of a drag-and-drop development environment. And part three, a proposal for modular architecture. We'll review in more detail how the software architecture influences the organization and some of the tools and technologies which might help it make modularity more achievable in the future. And as I mentioned, the overarching theme for this entire presentation is the question, how do we design an EHR platform that makes collaboration easy? So why don't we move on to the first part, part one, perspectives of OpenMRS 3. And it's healthy for any organization to be discussing the next steps. And there has certainly been an ongoing conversation for a number of years on Talk discussing potential new features. And when you go back, you can find Talk conversations on different technologies such as microservices, different proposals for ideas for what should be in 3.0, the idea of taking OpenMRS into the cloud, supporting functional disease, the idea of Kafka, Kibana, EHR sync, mobile responsiveness, a single sign-on, multi-tenant architecture. There's quite a long list of different ideas people have discussed over the years of what people might be looking for in the future of OpenMRS. And a few weeks ago, I proposed a heuristic to try to simplify many of the conversations which have already taken place on Talk, design calls, Scrum of Scrums, and different forums within the OpenMRS community. And the way that I was viewing it is that some of the conversations are applying to the current state, discussing reasonably urgent and baseline operations. Some of the conversations are talking about more upcoming priorities, things in the next 6 to 18 months. And third, some of the conversations are more long-term, talking about bigger vision objectives for the next 2 to 5 years. And I found it was helpful for me to go through some of the past archived Talk conversations and design calls, previous implementer surveys, and try to bring together a lot of what people wrote in these three categories, current state, upcoming priorities, big vision, and put them all into one single document in these respective categories. And so I've tried to go through and collect a lot of what's already in the community's resources and bring it into this one document. It's still a work in progress. The second thing regarding the OpenMRS wish list is trying to figure out a way to summarize some of the high-level themes. And certainly if you look at the Nairobi 2018 conference, there were some big themes that came out of it. The first is people want a system that is fast to implement, customize, and even configure without the need for developers to run OpenMRS. Second, organizations want to have shared libraries such as shared concepts, indicators, clinical workflows, forms, decision support tools, and reports. And ideally, these shared libraries would be disease-specific, such as an HIV set of workflows and forms or a diabetes set of workflows and forms. There's a request to have, of course, an intuitive user interface that works across mobile, tablet, and desktop, and that this should be able to be used at the point of care. It should be multi-tenant and support cloud installations. It needs to use advanced sync as well as offline capabilities in order to function in the different environments the system is deployed. It needs to have a straightforward data pipeline to be able to track indicators and move the data from acquisition to reports. There's, of course, need for interoperability with other systems, such as being fire-friendly. And there's consideration on how will new technologies such as PostgreSQL native, React Native or Docker play into OpenMRS. Others, of course, want the system to be modular so that they can combine the parts that they require as needed. And it should be able to handle billing, insurance, hospital features. And there's, of course, a strong interest in the very first version, maybe, of some of these improvements being specifically targeted at addressing chronic disease or non-communicable diseases, NCDs. And I think this wish list is awesome. And I wish we had all of this right now. But the reality is that no single implementer can build all of this. And no single commercial EHR vendor has built all of this. And no one will give us, $1 billion to be able to build all this from scratch. And so each of these ideas on the wish list is really actually a large boulder to move. It's quite a lot of work to implement any one of these wish list items, let alone, all 10. And this is just a summary of the many wish list items which are discussed. And therefore, I think that part of the reason that it's so hard to implement even just one of these large boulders is that every part of the system is connected to the other boulders and parts of the system, which sometimes makes it tough to go into OpenMRS and work with the system there. And therefore, at times when people implement new functionality into OpenMRS, rather than going in and implementing it in such a way where it works with the OpenMRS ecosystem, it's sometimes easier just to go build something from scratch and not have it compatible with the rest of the system. And this, of course, leads to increased fragmentation because different implementations build their own unique implementation-specific components. Which leads us now into this third part of the introduction, talking about the meta-narrative around fragmentation. As I mentioned before, there's this recurring theme I heard in Nairobi, which is of increased fragmentation within OpenMRS implementations over the last few years. And Burke did a great job highlighting this in his October 2018 presentation. And this increased fragmentation has, of course, led to different implementations designing components which only work for their implementation, and this reduces the ability of the community to exchange their parts that they develop. And it's very fortunate that there's now an interest to move towards collaboration. And I would just like to do a very quick thought experiment on the importance of moving from fragmentation to collaboration. So in one thought experiment, and these are just thought experiments, this is not a depiction of reality in its current state, but in one thought experiment, we would say that fragmentation increases, and this means that implementations continue to develop tools that are unable to be effectively shared across the platform. This reduces the ability of the platform to develop as an EHR, and over time, the quality and usefulness of OpenMRS decreases. The technology in the system becomes stagnant, and this makes it all harder for OpenMRS to become adopted as a technology system. It reduces the interest in volunteers to contribute to the platform. Fragmentation makes it difficult to fundraise for OpenMRS, and ultimately, the long-term stability of OpenMRS is uncertain, given this slow downward spiral of fragmentation. Of course, this is in contrast to another hypothetical thought experiment, which is where collaboration increases. And in that one, implementations develop tools that are shared across the platform. And so the overall quality of OpenMRS increases. It becomes more useful, easier to use, and the platform stays up to date with modern technology. This increased adoption of OpenMRS as a platform increases volunteer support. It makes it easier to do fundraising for OpenMRS. And ultimately, OpenMRS has a bright future, helping improve global healthcare as upward momentum continues to build through collaboration. And so the question is, from my perspective, how do we design an EHR architecture that makes collaboration easier? How do we design an EHR platform that makes collaboration easy? Which leads us now into the second part of the presentation, which is principles of modularity. But before we go on, I would like to just comment on the term modularity, because I've seen the word modularity used from everything to define a whole part of an EHR, such as acute care, to a specific user interface component, such as medicine reconciliation, to a specific disease subtype, such as tuberculosis, to a feature such as interoperability. And so to help sort of use different terms for clarity, I'll refer to the concept of modularity as the ability to combine isolated elements together. And a component will be a type of modularity which is specific to the user interface. And I'll use the term module more specifically to refer to software architecture elements, which are loosely coupled with bounded contexts, which have well-defined edges. And I'll use the term template when I'm discussing a configuration of these components and these modules with regards to a specific theme, such as hypertension or HIV. Now, of course, we could come up with probably much better terminology to use in the future, but it's just a way to think about different types of modularity with regards to the software systems we're talking about. And the concern, of course, is that people will use the word module to refer to all three types of these different systems, but I think these are separate. And we'll look at these in a little bit more detail in the upcoming section. But first, let's start by looking at modularity from the physical world and some first principles, because of course, I really like to always, when I'm starting a new project, try to observe the physical world and try to infer a few general principles. And there's 5 which we'll address today. The first observation is that almost everything in the world involves modular components. Wherever you look, there's modularity, the reusable elements coming together into larger wholes. Cells, tissues, organs, atoms, molecules, these are all modular components. The material used in the construction, the wood, the steel, the doors, are manufactured from. These are all manufactured with specific specifications and standard sizes. Even electronic devices are assembled from standard components. And so modularity allows for nature and for us to construct and build quickly and cost effectively. It allows for efficient and effective distribution of resources and labor. It allows competition and innovation in the marketplace. And so modularity really is a critical part of life, and it makes sense to try to incorporate modularity, I believe, as much into our digital world. Second observation, that we should understand the module's borders and boundaries. An important consideration when designing modularity is the boundaries and borders of the modular components. Consideration of what the extent of whether a particular element needs to work within an internal modular system, or if a particular element needs to work within an external modular system. For instance, in the 1950s, modular furniture systems became very popular, and now each modular system was meant to connect objects within the system, but you couldn't transfer elements between systems. And so this is a general principle to consider when designing a system. The second consideration is that modularity has well-defined small touch points and interfaces. And it is important to realize how, whether you're thinking of the light socket, a plumbing socket, or a screwdriver, that these modular systems have evolved to have very defined small touch points and interfaces, and these will change over time. The fourth observation is on standards and specifications, and that these are really the magic bullet behind our interconnected world. Many national standard bodies are part of ISO, International Organization for Standards, and standards ensure compatibility between modules, they ensure safety in products and services, and they help the sharing of good ideas and best practices. And literally everything has a standard behind it, whether it's on how to make ballpoint pens to how to make the pen caps to reduce asphyxiation risks. And the fifth and last of these observations is that I think it's really important to focus on the end goal and not the technology. Modular systems must be designed to allow both incremental technologic advancements within a module, as well as the entire replacement of the existing modules. Whether you're looking at the printing press or the telephone, each have undergone stepwise as well as leaps in its innovation cycle. But the overall end goal of both technology has remained the same. And therefore, as a general principle, start by focusing on the end goal when designing a modular system and not the specific technology, because the technology itself is probably much more volatile than the larger end goal. One other category of interesting observations regards the impact of modularity on organizational behavior. And it's really important, I think, to understand how modularity influences the organization of teams and companies. In software development right now and in corporate development, there's a lot of interest in moving towards 2 pizza teams. And these are, of course, teams which can be fed with 2 pizzas. That's generally considered 6 to 8 people, but no more than 12. Small autonomous teams can be more innovative, they can move quicker, and they can have greater product ownership. And the other advantage is that this gets around the tangled web of a large, slow-moving institution. And so modularity allows for a distributed governance model, and this allows each individual team to be more autonomous. Now, of course, this works on a macro level as well when you consider just distributed governance in the state of the open market. Any company can form its own company within the free open market system, and they can choose what problem they want to tackle, use their own expertise, set their own roadmap, and then connect with other companies as required. This would be in contrast to an economy where you might have a central planning committee which manages the entire economy, and historically we've seen that be much less efficient. And you could even apply these types of organizational behavior drawings to the concept of open source software, where in theory you probably have multiple groups which are working together to work on that open source software and trying to understand how you can build an organizational model which really promotes distributed governance makes a lot of sense. We now come to the end part about talking about modularity, and we apply it to electronic healthcare systems. There's been a lot of focus on interoperability between clinical data systems, between EHRs. And we've been making a lot of good progress in the last few years through the use of FHIR as a means to exchange healthcare data between systems. But because electronic healthcare records are large monoliths with many features, there is still a very high barrier of entry to the development of an electronic healthcare record. And because there are so many features contained within one single software product, there's very high switching costs for an organization to switch EHRs. And the combination of the high barrier to entry and the high switching cost results in a low innovation, low energy marketplace. And therefore, I believe that interoperability of clinical systems is not enough to get over these market failures and improve the electronic healthcare marketplace. What I think is required is not just interoperability of data between clinical systems, but interoperability of data and events within the functional components within an EHR. And this is really critical because what it means is that in theory, you could swap out the operating room scheduling component with a better one. And when an EHR is designed of individual functional components, each with their own bounded context and loosely coupled together, it means that the barriers to participate in this marketplace are lower. It means that it's easier for implementers, universities, startups, and businesses to take on the building of a specific component, which will then be able to integrate into the greater system within the EHR. And so you could imagine where one day in the EHR, it's composed of multiple different types of components. Some of them might be free. You might also have, in addition to the free option, a subscription model or a paid model which a company has produced. And now what's happened is each individual functional component can compete directly on its quality. And potentially in the more distant future, you might also have machine learning introduced through this concept of functional components within the EHR. But of course, achieving this level of decomposition of a monolith, achieving this ability to take apart of what we now have, which are very large systems, and break them down into functional components, requires quite a lot of work. And we need to understand the boundaries of what each of these components are, and then map the events and the interactions between these standardized subdomain boundaries. And as far as I can tell, unfortunately, as great as FHIR is, it hasn't yet done this. And so that's why interoperability between clinical systems is not enough. I also have a much longer article on this particular post if you're interested on the website, gregoryschmidt.ca. And we get back to our theme question of how do we design an EHR platform that makes collaboration easy? And we apply this to how modularity makes sense for an open source EHR. And when we think about modularity, we talked about how it can influence organizations and software. From an organization perspective, OpenMRS represents independent organizations and ideally has a certain distributed governance model to it. And you want a place where it makes it easy for new developers to start with the code base. And having a more modular code base makes it easier for new developers to come in because then they only need to learn the smaller part of the code that they need to work with. On the side of how modularity can influence software, modularity allows for more off-the-shelf elements, which, as we talked about in the fundamental concepts, off-the-shelf elements is really how you create faster and cheaper ability to build things. In addition, modularity, or this loose coupling of well-defined components, makes it easier to upgrade a particular module when required. You could also rebuild or swap a module if you want, or even write it in your own language or using your own database structure for that particular module, which doesn't have to fit with the database structures or the languages written in the other modules. And this makes it, of course, easier to upgrade technology. Now, as a way to take these sort of high-level concepts of modularity and how it influences organizations and software, why don't we look at a specific example, example one, of a modular EHR. And this is an example of horizontal and of vertical modularity. And this is a conceptual example. It's not a system architectural example. I just want to underscore that. And so, as you can see on the slide, at the bottom, we have the foundation. And the foundation is going to have the foundation modules. These are core services such as accounts, admin, security, compliance, offline, sync, backup, and mirroring, etc., etc. And on top of these foundational components, you are able to build your own application. And these actually are the tools that clinicians will use. And an organization may have a simple application for a community health worker and a bigger application for the rest of the clinic. And an application uses different user interface components. Now, these may be brought together based on the needs of the application. For instance, the community health worker application may need only a patient list and an access to a questionnaire form, whereas the chronic disease application may require a clinic queue instead of a patient list, also a patient list, and some access to forms, but also lab reporting, x-ray reporting, medication orders, and the ability to produce reports on the system. Now, on top of this, you could apply a disease template. And so a disease template applies to the user interface components and the application in the foundation. And for instance, you might have a hypertension disease template or an HIV disease template. And so, as I mentioned previously, this disease template would bring with it the particular sets of questions and workflows, reports and indicators, forms, and different elements you require to be able to run essentially a hypertension chronic disease clinic and populate your user interface components in your application and ensure they're properly aligned into your foundational modules. And so what we have here is vertical separation of all the elements as well as horizontal separation of these elements. And so this permits flexibility in deployment and in assembly. One other thing I want to highlight here is the anticipated turnover of these different elements will all be at different rates. For instance, the user interface components will likely be upgraded and rewritten probably every few years, just like any modern web or mobile application. And in order to be a developer who wants to work with these user interface components, you probably just need to know front-end languages. This makes it easier to come in, to rewrite a component to the specifications and the standards that that component has, and then hook up that component to the existing API gateway that populates it. At the other extreme, you have the foundational modules. And these, again, should also be upgraded and improved and expanded, but probably that will occur at a slower rate than the user interface components. And it also requires a different type of developer because it requires one with particular subdomain expertise, such as in sync or in offline. And then in between these two, you have the application construction level. And here you have developers who have an in-between expertise and are able together to bring the user interface components that are required and connect those to the foundational modules that are required to build a particular application. Now, in order to show how this could work in a little bit more of a concrete way, what I would like to show is how you could assemble an application using a drag and drop development. And so, although I discussed in the previous example that you could do this using developers, there's a lot of interest in trying to understand how we could use a more simplified installation and customization process. And so this is a very simple concept of a few slides illustrating that. The illustrations and mock-ups are really for the concept only and not the visual design. But what you'd have is an OpenMRS setup wizard. And when you log in, there's the first step of choosing your default settings. And so here you'd be able to choose audit logs, EHR compliance, security, single sign-on. Ideally, all of these would be pre-configured with logical defaults. It might inform you of ones where you have an error in the configuration and also tell you of which modules you don't have installed. The user could then go to organize their branding for their organization, choose appropriate language and time zones, and other geographic considerations. The user then might want to go and open the User Identities and Facilities tab. You can here choose your user identity, patient management, facility lists, and you move on to manage those other services connected to the medical record here, such as the medical database and the terminology service. I go back now to the OpenMRS wizard, and there are two ways which you could hypothetically build an application. The first might be to choose here a disease template, and in this case you could choose HIV program or hypertension program, and if you entered into this application builder through this high-level manner, what you could have is you're essentially coming in from this perspective on the diagram, meaning that if you chose hypertension, it would automatically select the required user interface components and application and foundational modules in order to deliver hypertension. Alternatively, and we'll go back here, the other way which you could enter into this wizard would be to, let's say, build a new application. And so in this case, you have the ability to choose a standard application, for instance, for clinic, for mobile or for hospital. And what this is doing is really approaching this from the other perspective, coming from the application layer, the application level, and choosing your desired user interface components. And so in this case, we'll click Clinic Application, and now we have the ability to choose the navigation structure that we desire, and we're going to go with bottom tab navigation. We can also then edit the tabs in their design. And of course, once you have a tab opens, in this case the Home tab, you can go and add in components. And what we are seeing here are homepage components, specifically for the patient list. And as we can see, there are two standard patient list components, the simple and the detailed patient list. And it also appears that other organizations have also added some other patient list components, such as AMPATH has a patient list here, and oncology also has their own specific patient list. We'll drag in, for our example, the standard simple patient list and put it in our app. Now, of course, we can go in and edit this component by clicking on it. And in theory, you could have a very simple set of ways you can edit this component. For instance, this one you may be able to change the display from a stack or table to flip cards. You might be able to toggle which types of patient information is displayed on the patient list. And then you could also display what type of action buttons are available with each patient's list. Each user interface component can subscribe to standard data streams for data queries. And of course, this would ideally be able to be customized in a very simple way to connect essentially the data source or the data filters up to this component without requiring the need of detailed knowledge of the code. And finally, of course, your custom filters, you might have other options on ways you can customize a component. For instance, you might be able to turn on the ability to sort and filter that component. You might be able to turn on pagination and then edit how that pagination looks. But you get the general idea. This is a very rough concept, but you can see that you have a default component, and then within that component, you can turn on and off different features and essentially just hook it up to the right data stream that you need to populate it. We'll go back now and look at adding a patient search component. And so we'll click and bring in the standard patient search to our application. And again, you would drag it over, and it's the same concept as before. And you could imagine how you would have, let's say, a very large library of components develop over time. And you would ideally have standard components, which you could build a complete comprehensive application. Over time, those individual components would have new versions, which people would continuously design and upgrade. And then as required, institutions and groups could develop their own components, which aren't part of this library, and also share them into the component library, making it easier for other groups to get up and running, and also have the required specifications for each component so that anyone knew what the minimum standard to build that component is. Why don't we move on now to the next part of this OpenMRS setup wizard, talking about adding a new clinical form. In this hypothetical drag and drop example, you have the same ability to design a clinical questionnaire or a clinical workflow questionnaire using the drag and drop elements. Now, of course, this is a video that you're seeing on screen from SurveyMonkey, but it's the same idea of what could be built in OpenMRS, where you had different default question types and different elements, such as a view of a labs or view of medications, and you can order them as required in the form builder. And of course, ideally, you would then have different standard components which could display the form builder. And you would ideally want the forms to be coded in such a way that any form viewer could pull any OpenMRS form design, form content or form schema. We'll move just to the very next one of these categories, which is on automation and logic. And it's important to realize that standard business software such as CRMs or chatbots or email marketing, really thrives on the ability of a user to create their own business logic without needing developers. And what we see here is a screenshot of different types of business logic builders. And if you like any of these screenshots, I have a document with over 100 pages of these examples. And a very popular tool is Zapier, and it makes it easy to integrate APIs from different companies all into a single workflow. My brother essentially used Zapier to create a 7-figure business in under 18 months. And being able to bring together different software tools through their APIs and create automated processes and interactions with ease. And I think that there's a lot of powerful things that we could do in healthcare if we had the same ability that the business world has in their integrations. For a very simple example, you could imagine that when a new patient checks into a clinic, that you may want them to have their ID printed out. You might want to send a consultation to the dietitian. You may wish to send a requisition to the insurance or operation. And all of these components could be brought together and automated with a logic orchestration sequence, which could be visually designed, again, allowing groups to customize and implement their operations without requiring developers' support. And maybe in the distant future, this is something that could also be within OpenMRS. And of course, this is an example here of Zapier on how you can take this QuickBooks invoice and then automate it as part of a sequence. One last part we should talk about is editing and the style. It's important, I think, that all these components we've been talking about in this user interface mockup have an agnostic style. And they would, therefore, you would have an overriding application style editor where you set the styles for the entire application, and then the individual components would adopt that style. Now, in order to create these types of flexible components, there is a technology that may be helpful, such as web components, but we aren't really going to discuss it in much detail today, other than saying that it has the potential to allow one to develop a user interface component that can be shared across multiple different language frameworks and be essentially language agnostic from this regard. Unfortunately, the web components are still reasonably early technology. They still don't work as smoothly with React, but it's definitely something to keep an eye on. Of course, the simple workaround would be to say, well, we'll adopt one particular language to develop all these components in, and that will be the first way to build one of the first applications. And then if another organization wishes to develop an application using a language different, such as if one group wants to use React and a different group wants to use Angular, perhaps both languages will each have their own library of user interface components. And I think this is really cool when you think about, again, this horizontal and this vertical modularity and how it can impact the software platform. Essentially, the goal is to be able to have these different levels being developed by different personnel, those who are developing disease templates, user interface components, application integrations, as well as foundational modules, really are different types of expertise, different types of development, and could ideally happen through different organizations and different individuals collaborating around the world. And by separating out these not just vertically, but also horizontally, you can allow each individual subcomponent within a particular user interface component be developed individually and upgraded sequentially. And so those are some of the general principles of modularity. And I think it's important, though, to realize that modularity can't remain at the user interface level alone or at the disease template level, and that there will be a certain number of benefits by also thinking about modularity at the deeper code system architecture level of the foundational modules. And therefore, what I would like to do in part 3 now is propose a few different ways which system architecture influences the organization, and then discuss a few specific technologies that might be of benefit in helping increase modularity. And I think there's an important disclaimer here that I'm not a system architect, and so everything you hear, take with a huge grain of salt. My hope, though, with this section is that I can show some of the benefits of increased modularity at the code level and how this can potentially influence the goal of modularity. But of course, we really need real system architects to weigh in on this. And if you are interested, and of course, a lot of the graphics we're going to see in these next few slides, they come from this textbook here, Microservice Patterns by Chris Richardson. It's a really good read if you want something which integrates a lot of the microservices as well as the associated technologies all into one single book. Otherwise, there's quite a number of YouTube videos you can read instead. So why don't we start? I think it's important to realize how architecture influences organization and processes. And again, this comes from Chris Richardson, this general principle. But what we have is architecture, and it can influence, as we've said, organizations and processes. And so one architecture type is one where you have loosely coupled modularity with well-defined boundaries and interactions. And what this allows you to do is to have autonomous teams. And that's because each team knows what its boundaries are and knows how to communicate to other teams if it has to, but it otherwise can operate independently. And the ability of having this type of a software architecture and this type of an organizational structure allows you to have a process where you can have a safe and continuous deployment of software into a large and complex application. And so Amazon at one point years ago was known to be committing changes to their software every 11.6 seconds. And the thought is that it's because they had this type of an architecture and organization. This is in contrast to an architecture where you have a coupled monolith. In this case, you require coordination and effort between teams in order to develop everything, because everything's interconnected, kind of like a large ball of spaghetti. And therefore, this tight coupling and the coordination required between teams results in processes which are at high risk to break things, and therefore this results in slower release, and the releases are more risky because of the chance to break things, and ultimately this leads to an avoidance of upgrades. And of course, avoiding all these processes just means that an organization avoids them more, and therefore each subsequent release is less and less often and is at higher risk to break things. And so the key takeaway is that software architecture not only impacts the software, but also the organization and its processes, and especially a lot of these other things which we don't consider, such as maintainability, extensibility, and testability. What I'd like to do now is to introduce the M word. I've been using the vague phrase loosely coupled modularity with well-defined boundaries and interactions to date, mostly because I think the purpose of this presentation is to emphasize modularity as a general organizing principle to strive for. And I think there's a lot we can do within OpenMRS already to increase the place where we can have modularity, both horizontally and vertically within the platform. And we can do that, of course, without using microservices. But I think it is worth bringing in the M word or bringing in microservices just to present it as one of the potential technologies which could help increase modularity. And now, this presentation, the goal isn't to say that we should move towards microservices or that we shouldn't, but it's just to explain briefly what microservices are, some of the associated technologies, and potentially how this could help with modularity. And because we're short on time, I entirely realize that this is going to be more of a general introduction, and it's not really going to go into all the downsides and complications of these technologies and probably why many of them increase complexity and are a bad idea. All right, we'll start now with looking at the system architecture, looking at the software. On the left here, we see the architecture as a monolith. Now, you'll probably be a little bit more familiar with a three-tier system architecture, a database, an application, and a presentation layer. But sometimes this more hexagonal pattern might be a bit more useful when representing modern applications. And in this monolithic pattern, what we have in the core, in the center, are multiple services with their business logic. Now, these communicate with the database, often MySQL, and this is surrounded by ports and adapters that communicate to third-party applications as well as to client layers. Now, it's important to realize that this entire application is programmed in one language, and of course, choosing what language to upgrade to is a huge undertaking and therefore would result in organizational standstill in the use of old technology. And this is in contrast to a system where you have microservices, where in theory you have each subdomain has its own service, and each service has its own private database, and you can use on that database MySQL, Postgres, GraphDB, Elasticsearch, whatever type of database is most optimized for that particular service. And this allows you to experiment with new technologies, and it also allows you to avoid operational standstill. Similarly, because all external communication within this service goes through the service's API, it allows you to write the code for that service in any language. And so you might remember the app called Wunderlist, which was acquired by Microsoft. Their CTO allowed developers to literally write in any language the developer wanted that day. Now, I'm not saying we should do this. I'm not saying it's a good idea, and perhaps OpenMRS could adopt several preferred languages, such as a JavaScript or Node.js or React Native or Python. But the general concept is really cool because, again, when you're thinking about how it makes it easier to upgrade to new technologies, this is a way to do it sequentially over a larger application and not have to get into operational standstill where you decide what will be the language we rewrite the entire application in. Now, don't forget, in the old version, there was one database which was being shared throughout all these different services. And therefore, if you change the schema of this database, there'll be numerous other interactions and complications of this. Whereas, again, because each database is behind the service's API in a microservice, it allows you to change the schema if required without breaking things. And there's, of course, ways to build your APIs with backwards compatibility. And so you get the general idea on how microservices permits collaboration, permits innovation within each service, and greatly simplifies the upgrading of components. Also, in theory, in microservices, a bug within a single service also isolates that fault, whereas a bug within a monolith potentially could bring down the entire application. And so we have here this example of distributed governance, which is really wonderful, as opposed to centralized command. And of course, just when you're thinking about this from a practical level, again, on the monolith, no single developer can hold all of this in one person's head. Or if it is all in one developer's head, it takes a very long and steep learning curve to get there. Whereas within a distributed architecture, such as microservices, it's easier for new developers to come in, to learn the code required and the APIs for their particular service that they want to work on, and then contribute towards that service in a meaningful way, knowing that they aren't going to break other parts of the system, and knowing that they're able to master the domain that they want to work within. So modularity has these advantages. Again, thinking about how modularity influences organizations, we see here on the left where you have a monolith trying to coordinate its upgrades. And of course, testing the integration of multiple different software teams committing their code is very tricky. And then the other trouble is that after deployment of a monolith, if you had another set of services that relied upon the monolith, but perhaps are separate from it, those services may have not been tested and might break with the upgrade. This is in contrast to a microservice organization, where each autonomous team is able to reliably develop and test and then publish their own code. And because this architecture is loosely coupled, you have more confidence that you won't be breaking things in this process. Now, of course, some may suggest that service-oriented architecture is actually just microservices, or microservices are just service-oriented architecture, and there's really nothing new here. I think the problem, as Martin Fowler would say, with the term SOA, or service-oriented architecture, is that no one knows exactly how to define SOA. And it's probably worth considering microservices as a subdomain within SOA, specifically a subdomain where you have loose coupling. Now, if we looked at SOA architecture, you have a few major differences from microservices. First, SOA typically has a centralized database, and it also typically has an enterprise service bus, an ESB. And the enterprise service bus contains quite a lot of logic within it in order to know how to route messages between the different services in a service-oriented architecture. And so the combination of the single shared database and the enterprise service bus with its logic ends up resulting in a system which is still quite coupled together. This is in contrast to this slide, where we see a microservice approach where you have each service having its own well-defined boundaries of that particular domain, its own database and logic, and then it interacts through, as what Martin Fowler would call, our dumb pipes carrying these messages. And the actual services have the smart ends to interpret the messages which are being carried. So here it's considered loosely coupled with well-defined boundaries and interactions. Now, understanding exactly what these modular boundaries are is certainly tricky, part of microservices. And there's different approaches on how to define it, whether you use business capability or domain-driven design. But the key theme is that the subdomains within the industry are carved out, and then the microservices represent that subdomain. Now, of course, microservices are a bit of a misnomer. They don't actually refer to how many lines of code the service should have. But this is tricky because you need to kind of understand the whole domain to be able to do this type of work. And there's lots of other considerations, such as the volatility of that domain to change, which part of the firewall it's on, understanding its data consistency issue, understanding who's going to build it. Will it be an NGO or a private industry? And it's, of course, a bit of an art and a bit of a science. One other part which needs to be considered is the communication protocol, and trying to understand exactly how these dumb pipe system will work. To greatly simplify a lot of the complexity of communication protocols, one way to think about it would be to imagine communication protocols being either one-to-one or one-to-many, and either being synchronous or asynchronous. And so an example of a synchronous one-to-one messaging might be something such as REST. And the problem, though, with REST, as great as it is, especially for external services, that some of the downsides are that both services need to be available, and you need to know the message delivery location. This is in contrast to another type of communication pattern, such as broker-based messaging. An example would be Apache Kafka. And in this case, it handles both message storage and message queue and publishing and subscribing. And this essentially greatly reduces the need to know where to deliver the message. And then the software, such as Apache Kafka, handles the buffering of messages and guarantees delivery of messages, which has, of course, as you could imagine, benefits. Now, one of the other technologies which is worth considering with these types of patterns is that of event sourcing. And it's a really cool architectural pattern because instead of updating the database directly, you update the append log. And so think about this like an accounting ledger or GitHub. Your bank account is based on summing up the deposits and withdrawals from the month. And if you lost your monthly total, you could rebuild your balance by adding up each transaction throughout the month. And in the same way, the application state can be blown up at any time and rebuilt by replaying the events. Now, this comes with some really cool benefits. For instance, it pairs really well with the event stream model of service interaction. Kafka is an append-only message broker. It also provides a built-in audit log, which is a critical part of electronic health records. It works well for offline, and this helps resolve some problems with syncing date stamps. And it provides a really cool time machine because it's in theory, you never delete medical data, which, as Clem McDonald's insisted, this is really critical. And event streaming is kind of the deluxe version of never deleting medical data. And of course, this model fits in well with certain orchestration logic patterns between microservices. There's a lot of downsides. Very briefly, of course, it adds a lot of complexity. There's a whole new learning curve. It's trickier to delete data. Imagine how your bank refunds money when they make a mistake. It's much harder to query this type of data, and of course, it's slow to rebuild these types of tables. But there are workarounds, such as snapshots. If you think about the fact that you get a monthly bank statement, that is essentially a snapshot. And then you can infer your future account balance based on snapshots. And then there's also a data structure such as CQRS that might help, or a data pattern. And we can discuss that a bit later. And so here we have in this diagram each microservice using an asynchronous publish-subscribe model to publish services to the event history to the event store, such as Apache Kafka, and the event store acting as a message broker and database. So the stock microservice is listening for updates from this event store. The product microservice is pushing updates to the event store, and the order service is both publicizing and subscribing to the event store. Here's an example from retail where you have different services with different databases in their respective areas, creating streams of their data, such as a point of service stream, an inventory stream, and a remarketing stream. And then you have different services listening on particular streams for event data, and then each service knows how to handle the event data when they ingest it. We mentioned CQRS, or Command Query Responsibility Segregation. And what it is it separates the write service and the read service into two separate objects. Although they might use the same data, they're actually potentially using two separate data models. Here you see the command service writing data from the application. This data is then processed and transformed into another store. When the application wants to go read the data, again, the application user interface, it uses a different object to query, and it's querying a different database than that which was written. Now, why would you do this? Well, one, it works really well when you have asymmetry between your read and your write requests in an application. And so that in some ways allows you to scale read and write servers separately if you were on a network. And EHRs in general would have an asymmetry in their read and their write. It also pairs really well with the event sourcing data model because it provides now a reliable method for being able to speed up your read times. And it also helps with eventual data consistency across complex databases or microservice data. Now, of course, the risks remain the same. You have increased complexity and there's lag and data consistency troubles. But I would like to present, a very quick example of Ampath, which I think would be a strong exaggeration to say that we have an advanced CQRS and event source system, but there are some general components of CQRS that we have adopted or the team has really built out here. And so we're using Apache Kafka, Apache Spark, and the Elastic Stack. And what happens is on the tablet, using the point of care system, users enter data. This comes in through a REST API into the OpenMRS database. And then out of that database, using these different technologies, we produce a series of flattened calculated tables, which are processed, properly formatted. And then those tables ultimately become the endpoints which are queried when the application wants to receive data to view, for instance, a history of the patient's encounters or a history of a patient's set of vitals. And so we have found it has been helpful to separate the read processes from the write processes for many of the different elements contained within the EHR. Of course, I'm not proposing that all of the EHR should be event-sourced or CQRS, but in certain parts of it, it might be helpful in trying to understand modularity. The fourth example of a detailed modular EHR structure is still in development. I think a really key part of being able to understand modularity is trying to understand what the subdomains within an EHR are, because then once we have the subdomains, we can map out what the interactions between these elements are. And as I mentioned, I think that although FHIR is extremely helpful, it, from what I can tell, doesn't provide clear guidance on how the modular services would fit together, as we've been discussing previously about creating interoperability within the functional components of an electronic healthcare record. And so there's a lot of draft work already in development on this theme, trying to summarize these functional requirements into one place. But the document's not ready yet. But I look forward to trying to at least collect the functional requirements into one place so that then we can take this document of functional requirements more to a system architect and receive their feedback and expertise in trying to understand ways to divide it into subdomains. Now, of course, are there downsides to all the technologies we've been discussing? Certainly, and we don't have time to go into them. But in general, the big downsides are that we're moving the complexity from the tangled spaghetti code base into a complexity in deployment. And this really highlights the need for competent development operations, being able to manage automated testing and automated deployment. Many different speakers recommend not even touching microservices until an organization has really mastered automated testing and finally tuned their deployment. Of course, another downside is that event-source data and CQRS patterns are new to learn, that whatever architectural system is developed needs to be able to be deployed on a lightweight laptop running on a server in a remote clinic. And this is all uncharted territory. And just to really underscore that, there is no known example to date of an open source community moving from a monolith to a microservices. And we know this because Professor David Taibbi in Finland has been studying microservices, and he's asked on ResearchGate, Quora, Stack Overflow, if anyone knows of an open source project that has migrated from monolith to microservices. And he has a GitHub page where he's tracking this, and he's had input over the last year with different collaborators. And as of last week, the answer remains no. An example has not been found that we could study from and learn from. If there was interest to try to decompose a monolith, there are different articles and approaches to this, but just the general principle is that you start with probably one or two very simple services that are not part of the current monolith, and maybe even services that don't require a data store. And through the development of these services, you practice operational readiness and automated testing and automated deployment in the monitoring of distributed architectures and its security and debugging it. And then you slowly move on to other edge services. And then eventually, when an organization feels comfortable building new edge services that minimize their dependencies on the monolith, they then begin to tackle some of the more core services, at that time rewriting those services where required, extracting high-value code when it can be done, and slowly moving more and more into core services over time. Well, that was kind of a whirlwind of part 3 here, trying to understand the deeper question of how do we design an EHR platform that makes collaboration easy, and proposing a few examples of specific technologies and techniques which might make that happen. If we go for a summary of today, now at the end of the presentation, today we had 3 parts. The first part on perspectives on OpenMRest, we looked at the enormous need and the wish list within the community to really advance the platform. And we looked at the issue of fragmentation and therefore the need to come up with a way to reduce fragmentation and increase collaboration. In part 2, under Principles of Modularity, it was proposed that modularity may be a unifying principle to help make collaboration easier. We looked at some high-level examples, such as horizontal and vertical modularity, and presented a drag-and-drop environment where the user can bring together the necessary components. And then in part 3, a proposal for modular architecture, we looked at how software influences organizations and a few examples of technologies such as microservices, event sourcing, and CQRS that might help create structures that make it modularity within the system more prevalent. Now, if we were to consider the next steps, I would suggest or propose that with regards to Part 1, perspectives, we continue to map the baseline, the 6 to 18 month, and the 2 to 5 year needs of OpenMRS community and try to integrate all this into a single document, because I think this will be really critical in being able to understand the areas of common interest in the next 6 to 18 months. On the principles of modularity, I think it would be helpful potentially if the community thought if modularity is an important part of reducing fragmentation, if modularity could help increase collaboration, and then looking for concrete and straightforward examples within OpenMRS where we can move towards increasing modularity. And ideally, we could find simple and areas which we could have a high yield and be able to execute within a reasonably short period of time just to see if increased modularity is a benefit. Now, of course, this is where discussion for the creation of shared user interface components comes in. I think there's a lot of interest of being able to improve the reference application and to be able to improve the user interface of the OpenMRS system, designing it in a modular manner as a high-yield project which could be executed in a short period of time, and being able to experiment with these principles. And of course, if that's successful, perhaps we could then move on to more complicated areas within the horizontal and vertical system, which could be more highly modularized. And then finally, under part 3, a proposal for modular architecture, I think the next steps would be to continue the research and development, to continue to map the EHR subdomains, the interactions and events, continue to seek expert advice within this area, and when ready to perhaps start experimenting and incorporating some of these new technologies to learn more about some of the ways that they can benefit, and to, of course, research many other technologies. And that was now, I guess, about just over an hour on trying to understand OpenMRS 3, understanding how we can design an electronic platform that makes collaboration easy. We've gone from high-level principles and theoretical ideas to very detailed software-specific patterns. But the general theme is that you could probably increase the horizontal and the vertical modularity of a system in order to promote better distributed governance, which might ultimately have a lot of benefits for an open source electronic healthcare record. And of course, the meta goal of all this is to reduce fragmentation within the platform, which is being defined as individual organizations creating functionality and components and modules which are unable to integrate and be shared with other implementations. Because I think at its heart, a lot of the power and benefit behind OpenMRS comes from the open source community and the ability for different groups to benefit from those components that other groups have created and those modules that other groups have created. And of course, OpenMRS already has a lot of modularity built into its heart. I mean, the whole module is a concept strong within the OpenMRS Foundation. And so this presentation is not to suggest that we don't have modularity, it's to try to ask the question how we can increase modularity and increase the decoupling of modular components, which allows for increased flexibility and use of them. If you're interested to read more about these concepts, you can go to gregoryschmidt.ca. which is the blog website. There'll be a picture of the illustrations from this presentation, as well as links to the original authors who some of these slides, which I have borrowed from, are used. I'd like to, of course, hear any feedback you have on this. You can email me or get in touch with whatever platform you find best.